delta T1 as x1 square plus L square the whole root minus L multiplied by AE by L, where A is the cross sectional area of teethers, E is modulus of elasticity of tether material. If it is steel, we already know the value of steel. X1 is the arbitrary displacement in surge degree of freedom L is the length of the teethers. Teethers are considered to be inextensible. So, delta T1 is increase in tension due to arbitrary displacement x1. Okay. To be very clear, this arbitrary displacement is considered as unity to derive the stiffness matrix. Now, having said this, let us write down the equilibrium of forces in surge direction. I request you to refer to this figure again. There are forces acting in the surge direction K11 and there is a component of this in the x axis. If this is gamma x, this value is also gamma x. So, obviously, I should say this will be T0 plus delta T1 of sin gamma x, because the vertical component will be cos gamma x and this is sin gamma x. So, K11 and this are opposite in direction as you see from this figure. So, write the equilibrium of these forces. You know, stiffness units actually is in Newton per meter, that is force per by displacement. So, if I want to find the force, I should multiply the stiffness coefficient by the displacement to get the force. I am writing the force equilibrium. Therefore, I should say K11 into x1 okay, should be equal to, you can see here this force will compromise, which will be T0 plus delta T1 of sin gamma x. But friends, please see, TLP has got 4 legs or 4 columns. Each column will have a set of teethers. So, each teether value is T0, there will be 4 such legs. Further, from the figure, sin gamma x is actually equal to x1 by root of x1 square plus L square. You can see from this geometry, sin gamma x will be x1 by root of this value, okay, this value. So, now substituting this, let us say call this equation 1 and equation 2, substituting 2 in 1, we get K11 as 4 times of T0 plus delta T1 by root of x1 square plus L square, equation 3. So, this is my coefficient which I obtained from the surge displacement. Naturally, no force in sway direction and therefore, K21 will be 0. Let us talk about equilibrium of forces in heave direction. So, I am talking about equilibrium in the vertical axis now, heave direction. So, you see K31 will be one component, K31 will be one component in the heave direction, and the vertical component of this will be T0 plus delta T1 of cos gamma x. Okay. So, now I want to write the equilibrium for this, which will be K31 into delta will be equal to T0 cos gamma x plus delta T1 cos gamma x. There are 4 such legs minus initial tension of 4, because I am looking only for the difference, right. Also from the geometry, cos gamma x is actually L by root of x1 square plus L square. So, substituting back, this is equation number, let us say 4, this is equation number 5, this becomes 6. So, substituting equation 6 in equation 5, we get K31 into delta will be 4 T0 cos gamma x minus 1 plus 4 delta T1 cos gamma x. Again substituting for cos gamma x, we say 4 T0 cos gamma x minus 1 plus 4 delta T1 cos gamma x by delta. This becomes my K31, which is going to be 7. Now, you know the value of cos gamma x, you can substitute them and write in terms of L by x1 square plus L square. Now, what is this delta? This delta is nothing but the set down. Okay. So, delta is the set down effect. So, naturally when you apply a force along x axis, the rotation about x axis will be 0. Okay. So, K41 will be 0 because no moment will be developed about x axis, as there is no force along sway axis, that is, since K21 is 0, K41 will be 0. Okay. Let us say like this. So, I call this as equation number 8. Let us talk about K51, the rotation. Okay. This is going to be, this is anti-clockwise about CG. Okay. Let us take the moment about the keel, right. So, this distance is h bar. So, I should say K51 should be actually equal to minus of K11 into h bar. So, this is equation number 9. The negative sign indicates that K11 develops moment opposite to that of K51, and K61 will be 0, no yaw motion, because as there is no moment about z axis. So, that is equation number 10. So, now if you look at friends, we have K11, we have K21, we have K31, we have K41, we have K51, K61. So, now in the K matrix of 6 by 6, the first column K11, K21, K31, K41, K51, K61 are now ready. Please understand, stiffness matrix is always derived column wise. So, the first column of the stiffness matrix is now derived from the first principles. Similarly, we can do for the sway direction. So, look at this figure. If you look at this figure, we have given displacement x1 along surge. So, now I should give displacement x2 along sway, where sway is along the y axis. So, having said this, by giving unit displacement x2 along sway axis, one can derive stiffness coefficients in the same manner as that of the first column. But let us keep a very important eye on the non-zero elements, or let us say 0 elements. Okay. If you look at the first column, we already said that K21 is 0, K41 is 0 and K61 is 0. Okay. K21 is 0, K41 is 0 and K61 is 0. It means no sway, no roll and no yaw. On the same basis, I should say no surge, no pitch and no yaw. No surge, that is K12 will be 0. Please understand how we explain K12. K12 is the stiffness coefficient, that is force in the first degree of freedom, that is surge, by giving unit displacement in second degree of freedom, that is sway, keeping all other degrees of freedom constrained. So, K12, since there is no surge, this will be 0. So, I should say K12 is 0. Since K12 is 0, I can expect that K52 will also be 0, it means no pitch. So, K52 will also be 0 and of course, K62 will be 0 because no yaw moment. Okay. Now, I am interested in finding out K22, which is similar to that of K11. See here K11, T0 delta T1 by this. Similarly, I can write K22 as T0 plus delta T2, okay, divided by square root of x2 square plus L square 4 times. You can see here I have only replaced this and this with second suffix as 2, okay, done this. Once I know K22, I can now find K32 also. So, that is going to be 1 by delta of 4 T0 cos gamma y minus 1 plus 4 delta T2 of cos gamma y, and K42 will be minus K22 of h bar Now, one can write negative sign is due to moment due to the fact that K22 generates moment opposite to K42. Okay. Now, I have got the second column, you know K12, K22, K32, K42, K52 and 62. I have got the second column. So, I can now say I have got the second column K11, K21, K31, K41, K51 and K61. I already have. Now, I have K12, 22, 32, 42, 52 and 62, out of which let us mark the zeros. This is 0, this was 0 and this was 0. Similarly, this is 0, this was 0, this is 0. Okay. So, first column is completed, second column is completed by giving unit displacement along surge, unit displacement along sway. Let us go for the third column. So, what should I do? I should give unit displacement along heave. That is good. So, let us do this. We will continue this discussion in the next lecture. So, the summary, friends, we are attempting to derive the stiffness coefficients of a tension leg platform from the first principles which we learned from module 1. We are deriving the stiffness coefficients of a TLP to get the stiffness matrix. We will also derive the mass matrix. Once I have the mass and stiffness matrix, I can find the damping matrix, I can find f of t, and then I can solve this problem, which I will explain in the subsequent lectures.